Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So this is a second video of LLM series in which we will see the overview of transformer architecture, right? So as we all know, the LLMs are built on the architecture which is called as a transformer, right? So let's understand this in the brief level. In the upcoming video, we will deep dive into each and every component in the dedicated video, right? So let's get started. So first of all, transformer model were introduced in the paper called Attention is All You Need in 2017, right? So all LLMs are built on the technique which is called as self-attention, which was introduced in this Attention is All You Need paper, right? So they were designed to address some of the key challenges faced by earlier models in the pre-processing, or you can say processing the sequential data such as text or time series. So before the transformer, we were using the models like LSTM and RNN, right? So they were the best to handle a sequence or time series data before the transformer, right? So as they say, unlike the predecessor, the transformer excel handling the long sequence of data efficiently and effectively, right? So the problem with this RNN and LSTM are they are processing your input in the sequential manner, right? So for example, if you have 5 words, so you will provide the first word, then there will be the LSTM cell or RNN cell, then it will provide some output. Then this output and your next word, both will be provided in the LSTM cell, and then next output will be predicted. That is how they are trained, right? I'm assuming that you know the overview of LSTM, right? So you can know the limitation of LSTM and we can see how the transformer is improving, right, or solving these issues. Okay, so that's why these models are not good at handling longer sequences. If you have short sentence, it was working very fine, but when it comes like sequence length will increase. Sequence length means the number of words in the sentence or number of input tokens you need to provide to the model, right? So that problem is very well solved using the attention mechanism and the transformer architecture, right? That's why these models are become a backbone of very state of the art models like GPT and BERT. Okay, so now let's see the what are the problem was with the earlier models, right? So let me first erase this. Okay, so when I say with the earlier models, I'm talking about the LSTM and RNN, right? Because before transformer, these were the model which were using for the sequential or textual task. Okay. So as I say, before transformer, recurrent neural network RNN and long short-term memory LSTM were go-to model for sequential data, right? So there were first problem was sequential processing. So as I say, we are processing one token at a time. So you cannot get the faster output, right? Because every sequence will be processed at a time in the sequential manner, right? So it will be very slow. Second thing, the vanishing gradient problem. So LSTM has a lower issue with the vanishing gradient, but the RNN cell, which was the predecessor of LSTM itself, it was facing the issue with called vanishing gradient because we are backpropagating over time in the RNN or LSTM, right? But still, LSTM mitigates this issue at some level. But when you have longer sentence, right? Let's say you have the 1,000 token, sorry, not the 1,000, but let's say 100 tokens in the sentence, and you need to process them, right? Then at that time, it can struggle with vanishing gradient problem, right? Or it cannot handle as well like dependency, because for example, let's say you have 100 words, right, and then you need to translate them into some word. That might be the case. Let's say a 50th word is dependent on second word, right? So to get this relationship, it might not work well because it will face the issues when we are using a long sentence or long sequence length, right? That is the issue also solved in the transformer architecture. And the third was a limited parallelization. As I say, like this is sequential model, right? So it cannot be parallelized to effectively utilize the GPU or the computational power, right? And the transformer we can parallelize a transformer architecture, or you can say transformer model, to get the output, right? So now let's see the how the architecture looks. Okay, so if you go, so this is the architecture of transformer model. So basically it has the 4 to 5 components. First you can say tokenization, second is the embedding, then positional encoding. We'll see in the brief, and encoder and decoder, right? So let's see in this image first of all. Okay, so first there will be the input. To provide the input into the model, we need to convert it into a tokens, right? So here the tokenization, they are using a technique called byte pair encoding, right? In next video we will see how this encoding technique works. So this basically we are dividing our text into smaller part which called as a token, and we are providing a ID to them, right? For example, there is any word like say hello, then hello will be provided ID, let's say 206. Then whenever the 206 is there, it will be replaced by the hello, or hello will be replaced by the 206 for the numeric form, right? So this is how the tokenization work. We will see in detail in the next video. Okay, then these tokens will be converted into the embeddings, right? Now we converted the text token into embedding. Embedding you can consider as a dense vector which is representing that word in the high dimensional, so the with the semantic meaning of it or the contextual meaning of it, right? So for example, if there are word car and let's say a vehicle, right, then these two vectors will be very similar in the high dimensional space because they are sharing meaning, right? The car is a vehicle, that's why. So don't worry about it, this is only the brief. We are going to see in detail how these all things are working, right? So this is about the embeddings. Then there is a positional encoding part. So if you see in the, as I say, in RNN and LSTM, we are processing one by one token, right? So if there are 5 tokens or 5 words, let's say, so we are processing one by one. So model already know which words arrive first and which word is at the second position, right? But here we are processing all input at a same time, right? So input can be whole sentence. Okay, if you are let's say there is a sentence hello world. Okay, so this both words will be passed together. Here is the input. So when you process here something, the model will lose the information that which word is arrived first, right? Because here we are using self attention and other part which are nothing but the multiplication and addition kind of thing. Okay, in the neural network, if you see, everything is related to multiplication or addition, right? So at here we will not have the information that's which word is at which position, right? So that's why there will be some positional encoding introduced in this paper. They are adding some vector into the input embedding which will preserve the information of the position each word, right? So that's why we require the positional encoding. We will create the dedicated video on this as well, right? So if you haven't subscribed my channel, please subscribe it and press the bell icon, so whenever I upload the new video in this series you can get the notification. Okay, so after this, so till now we tokenized them, converted into embedding, and then added some information for the position, right? Now there is a main part which is called the multi-head attention, right? So as I say, the attention is all you need paper, provided the technique called self attention, right? Self attention. So this is a slightly, you can say, modified version of self attention. Inside the hood it is the self attention itself, but we are doing it at the multi-head attention to save some time and process faster. Okay, we will see how self attention work and what we are doing with it so we can get the multi-head attention, right? And then there is a add and norm. So add and norm is nothing. So if you see from here, we are passing directly the here, right? This output, basically this output will pass directly here, and we are adding and getting the normalized vector. Okay, so if you say this is called like skip connection, right? Or you can think as like a residual connection which we had seen in the ResNet video, right? When we need to pass the information directly to the next layer, we are using this kind of skip connection, and this will help to avoid the vanishing gradient problem and to pass the information in a better way, right? So this is added norm, and then we are using feed forward neural network. So this is a simple neural network which we are using like a simple ANN, right? Feed forward basically. And here also we are using this skip connection. From here we are directly passing here output, and this output will be processed by the feed forward neural network as well, right? So this is about the encoder. So if you see this image has two part, right? This one and this one. So this is called as an encoder part. Let me write encoder. So this whole part is called as an encoder. So encoder helps to understand whole input sequence in a better manner. Then it will pass it to the decoder. Then decoder will generate the output. Let's say our task is the translate, right? Translation. Let's say English. So we need to transfer into Hindi. So we will pass here English sentence. It will process and generate the output here of the encoder output, and then that output will be passed to the decoder, and decoder will generate the Hindi tokens of that English word, right? So if you see, this is all about the encoder. So there are two kinds of models are there. First is, you can say, encoder only, and second is decoder only, right? So if you use only this part of the transformer architecture, which is encoder, and you receive the output here, okay, and then it will be called as an encoder only model. So like bird is one of the example of encoder only model. And if you use only decoder part, right, then it will be called the decoder only model, and a GPT is one of the example of decoder only model. Okay, so now let's see what happened in the decoder. So decoder is will receive the input from the encoder part, right? That will be passed to here. So it also has some mask attention. We will see what is the mask attention in upcoming video. Basically what we are doing at the high level. So in the output also we have some tokens, right? Let's say there are three tokens in the input. There will be two tokens in output in the Hindi word, let's say. So whenever we are passing here, when we need to predict first word, right, then we will mask these two part, okay, at the first iteration. So model will predict this, and it will not see this sequence. When we will train the transformer kind of architecture, we will get the better idea. But you can see whatever we don't need to show the model when we are training, right? So we are masking that information. That's why it's called the mask attention basically. And multi-head attention is same as here, which is based on the self-attention mechanism, right? So then there is add and norm, which is you can say skip connection. We are taking the output of this as well and adding here and getting the normalized vector. Then this is basically, if you see here, two multi-head attention, right? So this will process a encoder input, or you can say the output of the encoder, which is provided to the decoder as an input. And here basically we are processing the output of the decoder, right? So if you see, let me scroll a little bit, okay, yeah. So you receive first, how the decoder works I will say. So the mask attention, add norm, feed forward is the same as the encoder, but at the end we have the softmax layer. Here we have the softmax layer at the size of vocabulary, right? So at each time it will predict one word. So let's say when we are predicting, right, some word, let's say it predicts some word, let's say I, okay, or token related, okay. So then this token will be provided again to here, right? So it will use the word which is predicted at the previous timestamp and the encoded information from the input which is provided by the encoder, and process them along and predict a second word. Let's say it will be I am, and then these two information will be passed and the third word will be predicted, let's say I am fine, right? So this is how the whole architecture works as a brief. So again here we are also using the positional encoding, right? We will see how it is working, but due to providing a position of each word in the sentence, we are using positional encoding, right? Rest is everything is same, like multi-head attention, add norm, feed forward, add norm, and linear, right? So this is how the architecture looks at the overview level, right? In next video we will see in the detail. So if you have any doubt, don't worry, you will get the clear when I am creating a dedicated video for each steps, right? Yeah. So we see the encoder, we see the decoder part, and these are the embedding, positional encoding, and tokenization, right? So this is all about the overview of the transformer architecture. So stay tuned for the upcoming video in which we will see in detail how each and every part is working, right? So this is all about this video. If you like this video, please press like button and subscribe my channel and press the notification icon to get the notification whenever I will upload the new video, right? Thank you.